Hello everyone. Welcome back to the problem solving session for the course of Diffusion in Multi-Component Solids. And the course ID is NOC 24MM17. And this is a week 10. As usual, so we will be doing a problem solving session in two parts. First part consisting of solving the recapping the or refreshing the concept that have been taught in the current session, that is in week 10. And next part we will be solving some of the problems which are related to assignments, as well as which will be useful for the other competitive exams uh, and this exam, final exams also. So those examples will be helpful for solving those questions also. Okay, let's get into the let's get into the week 10. So in this week 10, totally 5 lectures has been taught. So lecture 42 tells about the theory of diffusion. Lecture 43 tells about the experimental determination of interdiffusion coefficients. That's a Boltzmann-Matano analysis has been taught. And in lecture 44, analysis of interdiffusion fluxes in the multi-component couples. So this is for binary as well as the multi-component components also taught in this one. And in lecture 45, the various techniques for experimental determination of multi-component interdiffusion coefficients also explained. That's other than the Boltzmann-Matano method, the other methods are also there. We will be discussing those things. And the experimental determination of interdiffusion coefficients from examples from the literatures. So some literature problems that have been already covered in our lab in current research is going on those things, and we will be determining the interdiffusion coefficients from those things. So this video series are helpful for the live application of interdiffusion coefficients, correlating the live application of interdiffusion coefficients and the theoretical parts that have been taught in the previous video lectures. They are merging with each other. It's a connecting link. So for example, in this one, so this video lecture is very important. That will correlate the application what you learned in the previous video lectures, that will be taught in these things. And whereas in the this Boltzmann-Matano is widely used in the current research to determine the interdiffusion coefficients, and other than the Boltzmann-Matano method, so different methods also used. Sorfres method, SF method, where we need not to determine the Matano planes, so that will be more flexible. And one more is like interdiffusion coefficients at a Boltzmann. Yes, that's a Boltzmann-Matano method itself. A Cricaldi's approach, there's nothing but. And for the multi-component systems, by making the n minus one dimensional solids, and we can be determining the intersecting diagonally intersecting points. So these are the things that we will be understood by these lectures, and I will just refresh those things for this video lecture. Let's start with lecture 42. That's theory of diffusion. I think I have improved my handwriting this time. It looks nice for me itself. So, in this theory of diffusion, so we will be learning self diffusivity, There are two type of diffusivity is diffusion interdiffusion coefficients. So inter not inter diffusivity values will be there. Though those are first self diffusivity, and second is impurity diffusivity, impurity diffusion coefficients. And next type of interdiffusion coefficient. Interdiffusion coefficients. Next is interdiffusion coefficients. And next is intrinsic diffusion coefficients. Okay, so we have two different type of types of diffusion interdiffusivities. So diffusivity values, and this one and this one. So this is for pure and homogeneous solution. So nickel. Okay, so nickel in, so iron diffusivity of carbon in iron, that is where the carbon acts as an impurity. So those things can be determined with the help of self diffusivity as impurity diffusion coefficients, whereas interdiffusion coefficients and intrinsic diffusion coefficients are totally different. So these are used for the multi-component solid alloys. So multi-component system. Okay, so these can be used for a kind of thing. So interdiffusion coefficients. What's the difference between interdiffusion coefficients and intrinsic diffusion coefficient? Please tell me. Here, yes. So I will explain. So here, the interdiffusion coefficients are calculated with the help of lab fixed frame of reference or volume fixed frame of reference. Whereas intrinsic interdiffusion coefficients will be determining the interdiffusion coefficients or determining the fluxes with a lattice fixed frame of reference or Krikindall frame of references. That's why it's called intrinsic diffusion coefficients. And here it is interdiffusion coefficients. This is the main importance between the these all the four values. Let's start one by one. How we are determining the self diffusivity values. Self diffusivity. So it's very simple. So what we will do is we will take a metal piece, Okay, consider the metal B. So it is deposited with another small layer of metal A. It is annealed. To diffuse this metal A into the B, we need to anneal it for some time. So we'll be doing annealing heat treatment. Then the concentration profile is generated. Kind of thing. It's generated. It's gradually decreasing. This is x equal to 0 to x equal to L or infinity. So infinity means, so the metal which is here is if not able to diffuse completely to the other end of the metal B. So to develop this one, the concentration profile, to develop this concentration profile, how it will be? So can you tell me, recall the equation? So I think, so this is the equation that we have already, pi dt, explained in the lecture 20, minus exponential of minus x squared divided by 4d into t. Okay, so taking a ln on both sides, ln c equal to k minus x squared divided by 4 dt. And by plotting the graph, ln c versus x square, so we will be getting minus 1 by 4d into t. This is the slope. I think we already explained this one in the previous example. So from this one, we know the time of annealing, how much time we have used for annealing. So that's why we know the slope from this experiment, and we will be able to determine the d value. So I will take that question one more time in this problem solving session. That will be helpful for understanding the and correlate the importance of self diffusivity. Next is a tracer diffusivity. Tracer diffusion coefficients. Here what we will do is, if consider the metal A, that is here the metal A is there, then we need to consider the radioactive isotope of this metal A. Then we will be doing the experiments, and we will anneal it and it will allow for the diffuse to the certain distances. Then A is equals to A into x square divided by, and by plotting the value of ln A versus similarly x square, we will be getting the slope, and which is in the form of minus 1 by 4 dt. So here d is nothing but d star. So we will be calculating this will be the slope similarly, but the method is different. So we will be using the radioactive isotopes for determining the tracer diffusivity values. Same way, if you want to determine the self-diffusivity value by tracing radioactive isotopes, you need to add the isotopes of same material. For example, nickel is there, you need to add the isotope of nickel itself, not other metal. So if you determine the diffusivity of sodium, you need to add the sodium isotope itself. Then you can determine the value of tracer self-diffusivity value. So this is all about the lecture 42. So next is, so this is very important, experimental determination of interdiffusion coefficients by Boltzmann-Matano analysis. First, in this lecture, I will explain how we will be doing the how we will be doing the determining the interdiffusion coefficients. Determining so first we will use the widely used method is diffusion couple approach. First is first first and foremost thing is we will be doing we'll be preparing the two different alloys. I'll make it in different colors so that it will be useful for you guys. So first I will make it in different way. Okay, so yeah, so this is material A and this is material B, or consider as metal A and metal B are prepared differently, or alloy A and alloy B, it depends upon the system. And what we will do is we will do the assembly of these two alloys, A and B, and these are supported with the help of some jigs, outer jigs, so that they firmly contact with each others. So after that we will be keeping in a furnace for diffusion annealing. So for a particular temperature as well as time. This depends upon the system. Okay. So anneal for particular temperature and time. After that, we will be taking out this and we will be bisectioning. It's only firmly joined. This metal A and metal B. I'll make it in different color so that it will be easy for you guys. So sorry, I have not got that color. I think so. Yeah. So this is the diffused zone. Okay. So what we will do is we will cut Sorry for disturbing. So what we will do is we will make an intersect. We will cut this both the alloys which are joined together. They are cut perpendicular to the interdiffusion along the interdiffusion zones. So after that, we will be analyzing. So this is the cut sample. So this is, if you say, this is a cut sample, and we will be doing a electron EPMA, electron probe microanalyzer, for the getting the concentration profiles with the distances. Consider this is distance and this is the distance. This is as x1 and this is x2. So what we will be doing is, so we'll be getting x1 and x2, and what you will be getting here, this side is A pure and here B pure. So this side is A is having highest one and it's reaching to the 0 here, this side, and here it is this side is B is having highest, and we will be getting the like this concentration profiles we will be getting for the and B interdiffusion zone, and this will be the zone that have been highlighted. So I will highlight both the things. So this is the diffused zone, and here it in the concentration profile uh, we will be doing the diffused zone here. Yeah. So one instrument that is used widely for this one is EPMA. You need to understand this characterizing instrument, which when mainly used for getting the high accurate concentrations. Quantitatively and qualitatively, you can get the both the analysis can be done in this electron micro analyzer. Here we will be using the wavelength dispersive spectroscopy. Okay, so wavelength dispersive spectroscopy used for the analysis of this concentration profiles. So Boltzmann-Matano method. So derivation is also already given in the video lectures. From there, we will be getting the minus infinity to plus infinity x minus x naught into dCA equal to 0. This is the criteria to get the Matano plane. This is mainly because of one assumption, that is, first assumption is the metal which is the elements which is present on the left hand side is diffused to the right side. Similarly, the mass balance has been occurred, like B atom, same amount of the B atom is diffused from B side to A side. The mass balance should be maintained. From that concept, we will be determining the Matano plane. Matano plane, it's a plane across which the mass balancing plane, it's also called as a mass balancing plane. Here where x naught is Matano plane. So most of the interviews or some other cases, so questions will be asked, what is Matano plane? You just tell me it. Tell that it's a mass balancing plane. That's a plane across which both the elements are diffusing, and it's a maximum flux plane also, where we'll get the maximum fluxes. And next is, so determining the interdiffusion coefficients. So to determine that interdiffusion coefficients, the formula derived is d tilde Here we are using d tilde because it's a interdiffusion coefficient. We determine the diffusion coefficients with respect to other components, not a self. You have to remember this one. So formula will be by Boltzmann-Matano method, 1 by 2t integration of c minus 2 c of x minus x naught into dci dc and dou c by sorry, dou c into dou x of x. Okay, so first, how we will be determining this one, let us understand those things. Okay, we'll change the color. So according to this one, this is the Matano plane x naught. Okay, so if you want to determine the interdivision coefficients at this point A, how you will be determining? First, you need to will write it below this one so that it will be easy. So if you want to determine the interdivision coefficients at point x A, so first need to determine the gradient slope of this one. By calculating the slope at this point, you can determine the dou c by dou x, and you know the time value, how much you have diffused, you have done carried out the interdivision so diffusion annealing. And next is integration of ci minus to c. This is your c value, right? X minus x naught, this is your x and this is your x naught, and dc. So that means this is the area under the curve need to determine to calculate this whole term. Okay, so by determining all of these things, you can determine the interdiffusion coefficients at particular composition. This is all about the binary system. So if you want to determine the for multi-component systems, for example, so if you have more than two elements on the both the side, so how we will be determining the interdivision coefficients? So that is explained in this lecture, lecture 44. Okay, L44 is talking about how these multi-component systems are diffusing with each other. For example, as we consider A and B atoms, A and B elements, we will be considering more than one element on the both the side. For example, here it is. This is concentration versus X profile. So before the diffusion annealing, this will be like this. So for confusing, so I will make it same kind of previously. This is one element which is having 60% of A and 40% of B. So one more alloy which is having 50% of A and 50% of B. Okay. So if you do the diffusion and if you get the initial concentration profiles before the diffusion annealing, so how it will be? So if you consider this is as the methanol plane, so this is assume it is 60 A and it is 40 B. So I will make it in different colors so that it will be easy for you guys to understand A and B. That's red. Here it is 40 B. Here it is 60 and here it is 40. And this side it is having 50. In between here it is 50 and 50. Okay, so both the concentrations are same, A and B, which is having 50. So this is the before the diffusion annealing. So after diffusion annealing, how the concentration profile will be developed? Let us see. Okay, so for A, this is the thing. One minute, I will make it a little bit wider. Okay, this is for A, whereas for B it is 40 and again here it is. I will make it a little bit down one so that it will be useful guys for understanding. So this is B and this is A. Okay, so this is from this concentration profile itself you will get more outputs. So this is the diffusion depth for a component, concentration versus X graph it is. This is diffusion depth and this is the methanol plane X naught or mass balancing plane. Similarly, we will be determining the interdiffusion coefficients and the fluxes is very easy. So for flux, we will be considering the j of x tilde equal to 1 by 2t integration of ci minus 2ci plus x minus x naught into dc. So this is the formula where we can use to get the interdiffusion fluxes. So this type of on the basis of this only you will get more questions. So how this concentration profile will be happening, let us discuss. To determine the flux of one component, you need to understand the concentration profile first. By explaining this thing itself, you can solve most of the assignment problems also. Assignment problems is depends upon mainly on these things. Consider only one flux profile and concentration profile. Yeah. So this is Ci minus, this is Ci plus, and what about this one? Yeah, this is the metanoplane x naught value. Now, what are the things you need to determine? First of all, if you want to calculate the for any particular x value, C of naught plus, it will be Ci of x. Okay, so Ci of x. If you want to determine the flux at particular position or composition, so if you are interested, similarly, this is the C of x. So need to first determine the area under this graph. That will brings about this one, and if you divide this one with 1 by 2t, you'll get the flux of at that point. Similarly, we are determining the all over the compositions, and we'll be getting the profiles kind of this kind of thing. Yes, this is at metanoplane. This is x naught, which is having highest flux value at this metanoplane. At this metanoplane. Okay, so one general thing you need to know that whether the, for example, I will give one more example for you guys that will be very useful to understand. Okay, now we will discuss that in the problem solving problems of this one, these things. And he is in the lecture notes. They have explained about the zero flux plane, where the flux becomes a zero. So if you got an uphill diffusion here itself, this is the metanoplane. So if this is the uphill diffusion that you got, and you will get the respective flux profile is kind of here somewhere. You get a zero flux plane. Not here, a little bit away from this one. Okay, so here you will get it. Sorry, here you will get it. Sorry. Yeah. So this is C versus X, and this is J versus J tilde versus X. This is zero flux plane. Zero flux plane. So what's the importance? Please let me know in the comment box sections. Okay, so after that, this one, the various techniques for experimental determination of multi-component diffusion coefficients. In this lecture, we will be understanding the Cricaldi's approach. Yeah. So Cricaldi's approach or extended Boltzmann-Matano method. For the multi-component systems, it's very difficult to determine interdivision coefficients. That's why for the more accurate value, so Cricaldi's approach is used. Approach is used to determine the interdivision coefficients for the multi-component systems. For a ternary system, if you have a ternary diagram, if you have a diffusion path like this, and one more is like this is a diffusion path, and this is the intersecting point, having a composition C1, C2, and C3. So, need to determine the interdivision coefficients at this intersecting point, and he has introduced these things. So, one J J1 tilde minus D dou C1 into dou X minus D tilde 3 1 2 dou C2 into dou X, so J2 tilde equal to minus 3 to 1 C1 into dx 3 to 2 dou C3 sorry C2 to dou X. Yeah. So one thing need to know that to determine these four interdivision coefficients, we need to know the values of J1, J2, C1, C2, concentration gradient of C1 and C2 in different position. So first, so these J1 and J2 are calculated from the previous equation that we have mentioned in the last slide. So we'll get a J1, J2, right? So after that, we need to determine the concentration gradient of first component as well as the second component at this intersecting point. By solving these two equations, you'll get the value of Yeah. So one thing need to know here it is. This is for couple one. So diffusion couple one. Different colors for that. Very easy. This is for okay. So you have four unknowns. Two equations is insufficient to determine the values. Okay. So that's why need to know diffusion couple one. You have first couple here 1, 2, 3, 4. This is for 1, 2. Diffusion couple 1, 2, 1, 2. So for diffusion couple 3, 4, the equation will be same. J delta equal to minus 1, 2. J to delta 2, 2, 2. No x. So you'll get the here two equations, here two equations, four unknowns, four equations sufficient for determining these values. You just need to compare the value for this one with this one. I will write it as equation number also. Equation 1, 2, 3, 4. Right? So need to compare, solve for equation equation 1 and 3. Similarly, equation 2 and 4. By solving these values, you will get the interdivision coefficients for the remaining all the four interdivision coefficients. For ternary alloy, we need, as we said, for ternary alloy, we need n minus 1 interdivision, n minus 1 square interdivision coefficients. By keeping n as a dependent component and ij as the independent components. For quaternary, it will be 9. Okay. For binary, it will be 1. This is the method, and body diagonal method has been explained in the video series for the quaternary alloy. So if you want to, so why we are considered the ternary system here? Ternary. So for n number of components, we need n dimensions of n-dimensional coordinates to determine the interdivision coefficients. For example, for the quaternary system, we need a 3-dimensional, sorry, n-1 dimensions. Here, for the quaternary, we need a cubic kind of thing. That is a three-dimension bidiagonal approach has been used. After that, last is about experimental determination of interdivision coefficients for examples from the literatures. So these are the current examples that we have carried out our research works in the labs and we got the from the literatures. So if you find any journals, if you find any papers, you can determine your own introduction coefficients and fluxes from those graphs or plots. Next is the problem one. Okay, so I will be giving a concentration profiles for these things. You need to determine the respective fluxes of. First one is very simple. This is first one. I think this maternal plane should be away from this one little bit. Okay, so this is also same thing. CI X naught. You just do this one. How you will be getting? Let me know. I think you have solved this. I assume you have solved this equation. Is these profiles? So the flux profile, I'll directly write the answer, and I will explain this one like this. Okay. Okay. One more thing. Why it is negative? According to the equation, you just leave this 1 by 2t x minus x naught c minus infinity to plus infinity into dc, sorry, ci infinity to ci plus infinity. Hmm? Yeah, according to this equation, if you consider the flux towards the right side of this x naught is x minus x naught is positive. So if this is positive, and whereas dc is also a positive. 1 minute. If you're moving from this to this side, okay, if you are considered towards the left side of x naught, x minus x naught is negative. See, x minus x naught is negative because x here is lesser than the x naught value, x value, x minus x naught is negative, then dc, final minus initial, is positive value. This is the final value that we will getting, and this is the initial value. This is positive. That's why it is negative value. That's why we got a negative value here. See, right? From here to here, x minus x naught is positive. When you are coming from this side, so if you are coming from this side, or if you are going like this itself, consider x minus x naught. So can you tell me the x minus x naught here? So here it is positive. Towards left side, this will be positive. Whereas what about the dc value? Final minus initial, that will be a negative value. So this is the final value and this is the initial value. That's why it is negative, approaching towards the positive. That's why it's the right hand side. So the flux is negative here. And one more thing you need to observe here, we have made flux at the end is 0. Why? So most of the questions will be asked because we are considered the infinite diffusion couples. That means diffusion depth is this much only, and beyond this one and beyond this one, the element is pure, like its own terminal alloy is there. That's why this is nothing but the infinite diffusion couples. That's why at the end of the flux is zero. Whereas here, flux getting zero here is different and flux getting here is different. Can you tell me what will be the flux profile for this? I'll write the answer first. Sorry. Okay, so here uphill diffusion is observed. This is nothing but the uphill diffusion. That means it's a very interesting point has observed by the Diana and Son. Uphill diffusion, the concentration is so diffusion will occur. Sorry, 1 minute. So diffusion will occur against its concentration gradient. Against its concentration gradient. The diffusion will occur against its concentration gradient. The gradient is like this, is moving towards this, but the flux, the it is diffusing a little bit up is observed. That means its own gradient is against its flux diffusion. This is mainly occurs due to the strong interactions between the elements. Here I have shown only one component. There may be another element, another concentration profiles, which will be affecting like this. So this element is affecting the division of other components. So this is the most fundamental thing that we need to observe in the multi-component systems, and most of them are will be neglecting this type of concepts.